density curves. A density curve is a graph whose area between itself and the x-axis is equal to 1. These graphs come in a variety of shapes, but the most familiar normal graph is bell-shaped. The area under the curve in a range of values indicates the proportion of values in that range. In other words, we can find probabilities by looking at the area between certain values in a density curve. Now, with density curves, we're working with continuous data. Let's think about a density curve that consists of two line segments. The first one goes from the point 0,1 to the point 0.41. The second goes from that point, 0.41, to 0.82 in the xy plane. Let's sketch the graph. So we're going to start at the point 0,1. And we're going to make our graph not quite to scale, just so we can see everything here. And it's going to continue to the point 0.41, and then it's going to go from 0.41 to 0.82. So now we will connect our lines. Now, before we begin talking about our percent of observations, let's verify that this is a density curve. So, if it's a density curve, the total area must be 1. So let's look at our area. Between 1 and 0.4, we have a rectangle whose width is 0.4 and height is 1. So this area is 0.4. If I draw another rectangle coming across here, again I have a width from 0.4 to 0.8 of 0.4 and a height of 1. So the area of this rectangle is 0.4. And then last we have this triangle whose height is 1, going from 1 to 2, and width is 0.4. Area of a triangle is 1/2 width times height, so this area is 0.2. So we have 0.4 plus 0.4 plus 0.2 gives us a total area of 1. So from this, we can find probabilities. If I want to know what percent of observations fall below 0.4, now this curve is not defined for below 0, so saying below 0.4 would be the same thing as saying it's between 0 and 0.4, or we can just say the probability that x is less than 0.4. And so that would be equal under a density curve. When we talk about probabilities or percents of observations, we're talking about the area under the density curve. So the area for less than 0.4 is this region right here, which we found to be 0.4. Between 0.4 and 0.8, those probabilities can be found by getting the area of this region that I've just shaded in green. And that would be 0.4 plus 0.2, which is 0.6. Now, if I ask what percent of observations are equal to a particular value, any value within our region, the answer is going to be 0. With continuous distributions, we have an infinite number of x values that we can have between our beginning and end of our density curve. And with an infinite number of possibilities, the chance of getting any one of those would be 0. So for these previous problems that we found, this is the same thing as asking the probability that x is less than or equal to 0.4, or the probability that x is between 0.4 and 0.8 inclusive. So again, these are continuous. In the previous section, we talked about discrete data with our binomial and geometric distributions, and those had different values whether we were strictly greater than or equal to, or less than versus less than or equal to. Those mattered for the equals. Let's look at another example. Consider a uniform density curve defined from x equals 0 to x equals 6. Well, a uniform curve will have the same height all the way across. So we're going to create a density curve that goes from x equals 0 to x equals 6. Now remember, the area under a density curve has to equal 1. So if we're uniform going all the way across here, our y value would have to equal 1/6, so that the area, your width is 6, your height would have to be 1/6, so that your total area is 1. So what percent of observations would fall below the x value of 2? So I'm looking for the x values that fall in this region. Well, our width is 2, our height is 1/6, so that would be 1/3, or 33.33%. What percent of observations lie between 2 and 3? Now we have a width of 1 and still have a height of 1/6. So 1/6 would be our answer. The median would be the place for the middle 50%. So where does this graph split in half so that it's 50-50? It would happen at x equals 3.